Hey there, so I'm Joseph, and this is the third part of the second chapter of Stewart's calculus. And we're going to be talking about differentiation formula, which are awesome because it lets us take derivatives of certain functions without using the derivatives definition, which can be kind of cumbersome, considering that it's a limit, and limits can be tough to solve. In the book, in Stewart's calculus, in chapter 2, they go through all the proofs of these formulas, so I'm not going to redo them here because they do a pretty darn good job of them in the book. I'm just going to tell you what they are and how to use them. So, I am going to write out just the list of all the differentiation formula that are covered in this chapter, because later on in the book there are going to be some more complex functions that you're going to get a formula for. But here are the ones that we're going to be talking about in this video. Alright, so we're going to be talking about taking the derivatives of constant functions, which are pretty easy. You can probably just think about how to do that right now. Second, we're going to be talking about constant power functions, like x to the anything that's a number. And 3, we're going to be talking about the product, and I put quotient in the parentheses because your book, Stewart's Calculus, talks about these two things as being different, but really I like to see them as the same rule, just kind of a little bit different. They're basically the same rule, and you'll see why. And then 4, we're going to talk about trig functions. We're going to talk about the 3 trig functions, cosine, sine, and tangent, and then their inverses, secant, cosecant, and cotangent. And we're going to learn formulas for taking the derivatives of all of those. So, let's start off with constant functions. So, we have a function that is a constant, f of x equals 2. This graph would look something like that, where that line is at y equals 2. Remember, the derivative is a rate of change. If you have a constant function, is it changing? No. So the derivative of any constant function is 0. Oop. That is a pretty easy one to learn. Moving on. So, now we have the constant power function. And again, your book goes through the proof of this. I'm not going to do it, but I'm just going to give you a refresher on what it is so that we can start using it, because it's super useful. So you have a polynomial, or actually not a polynomial, just the function, f of x equals x to the 4th. We don't want to take the limit of that. We really don't, because we'd have to multiply that x plus h term 4 times. That'd be horrible. But based on the constant power function rule, we can say that f prime of x is 4x plus 3, and the way I like to think about this before writing out explicitly what the formula says, you have the exponent, you bring the exponent down, make that a coefficient, and then you subtract 1 from that exponent, so we get 4x cubed. And explicitly this formula reads, if you have a function of ax to the n, its derivative, so f prime of x will equal an times x to the n minus 1. That's the formula. Pretty simple and super handy. You can use this for any polynomial, and remember, when you take the derivative of a polynomial and you just have a bunch of terms with constant exponents like this, you just apply this formula to each exponent and make sure that the signs remain constant, and you'll be golden. Now, moving on, we're going to be talking about the product and the quotient rule. Now, this rule is really important, and it can get really messy if you have long functions. And so I'm going to write out explicitly what this rule says right here. Alright, so here's the rule. We have the derivative of two functions f and g multiplied together, so the derivative of that with respect to x is that first function left alone as it is times the derivative of the second function, plus the second function, now we leave that alone, and we take the derivative of the first function and then we multiply them. So really it's a game of leaving one alone, doing some to the other, adding the plus the one that we didn't touch to begin with, taking the derivative of that and multiplying it by the one that we didn't, that we took the derivative of earlier, but then we leave that one alone. So just kind of look at that, take that in, and if this function talk is confusing you, these functions can represent just, that'll be 2x and this, is maybe like a trig function that's, sine of x, and then you're multiplying those together, and you need to use the product rule for that. And because we haven't talked about trig functions yet, that's going to be the next thing we talk about. I'm going to prove that this works to you by using two functions with constant exponents right here. All right, so say we've got a function f of x, and it is equal to, say, 9x to the 5th times 7x to the 4th. And you might say, oh, well, we can just multiply these out and then use our constant power formula to figure this out. Yes, we can, but I'm going to show you that the product rule works, and so we're going to do it both ways. And let's start off with the product rule way. So we're taking the derivative, f prime of x, and that is going to be equal to, we're taking the derivative of this one, so that's going to be 45 x to the 4th using the constant power rule, and then we're leaving this guy alone, so that's 7x to the 4th plus, and now we're taking the derivative of that, so it's 28x to the 3rd. Remember, constant power rule, just taking that down, multiplying it by the coefficient, and then subtracting 1 from that exponent. Then that would be leaving this guy alone, so that's 9x to the 5th. And so now we can multiply everything out. We get 315 x to the 8th plus 252 x to the 8th. Oh, that's nice. We get common exponents, and so that will equal 567 x to the 8th, and that's the derivative, right? Alright, and so now I will prove to you that so I'll write up the answer right here, that f prime of x ends up being equal to 567 x to the 8th, and I'm going to prove to you that that quotient rule worked because we're going to do it exclusively the power rule way. So remember, we've got f of x equals 9x to the 5th times 7x to the 4th, and now we multiply this out to begin with, and we will get 63x to the 9th. Remember, we can add those exponents. And now when we take f prime of x, you can get your calculator out to verify this, but you get 9 times 63, that is 567, and we subtract 1 from that 9, and that's an 8, x to the 8. Voila! The product rule works. And so the quotient rule is basically when you're dividing two functions and you're trying to take the derivative of that. So basically when you're trying to take the derivative of something where you've got one function divided by another. And the Stewart's book has this whole other rule for this, and I think once we learn the chain rule in the next video, and we use the product rule, just think about this as kind of an inverse of the product rule. So let's look at the function. Let's say we have f of x. I'm going to call that. We're going to call that 5 x to the 5th. And g of x, let's call that x to the 3rd. And so we're going to try to find that derivative. So let's have a big function f, which is equal to those two functions divided. And now, since this guy's in the denominator, we can bring this up and it'll have a negative exponent. And so that can be equal to times x to the negative 3. And now we can really just use our product rule to take the derivative. So we get the derivative of that, and that will be, first we'll leave the first bit alone, that's x to the 5th times negative 3x, and remember we're subtracting 1, so that would be x to the negative 4th, and then we leave this guy alone, take the derivative of the other one, and then we can simplify all that out to negative 3x plus 5x, because remember you're subtracting some exponents, and then that simplifies down to 2x. And so that's kind of the product rule applied to quotients. Alright, so the first trig function I'm going to show you how to differentiate is going to be sine x. So we're going to be trying to find d dx sine x. We're going to try to figure out what that is equal to. Now, again, your book has a really nice numerical proof for this, and it's pretty helpful in explaining what's going on, but I'm not going to do it again because your book has it, and presumably if you're watching these videos, you've got the book. However, I will go through the graphical and kind of conceptual proof for how this all works out. So let's look at a graph, and this is actually a picture that is from your book of a sine graph, of a sine curve. Okay, here we go. This looks pretty familiar. And you know from the previous chapter that when you've got a maximum point like this, the tangent line is going to be completely horizontal. Or in other words, the derivative is going to be 0 there. So, for the sine curve, we have, so the derivative is equal to 0 here when x equals negative pi over 2. See right there, negative pi over 2, pi over 2, and then, you know, you can infinitely add pi to all these values. And there you will have minima and maxima where the derivative is equal to 0. Well, what other function, that would mean that the derivative of this function has zeros, so points where it crosses the x-axis, at these points. Well, what other trig function has a 0 at negative pi over 2, and so forth? Well, let's look at another common trig function that's cosine. All right, so here we got cosine. And look at this. It has a 0, so equals 0 when x is negative pi over 2, pi over 2. You keep adding pi, and that's where its zeros are. So we can see kind of intuitively that it would make sense for cosine to be the derivative of sine of x, because all the places where the derivative of sine of x are 0 are places where cosine of x are 0. And you know, there is a numerical proof for this, but this should kind of give you a good sense and kind of understanding of why cosine is the derivative of sine. And so, although I'm not going to be doing the numerical proof for this function, in the proof itself, there is a bit where we get down to the limit as h approaches 0 of sine h over h. We can prove this, but it's really helpful for the rest of this course, and especially for the AP, to just know that that is equal to 1. Just remember that. That's something that you're going to be asked on the AP, and it is really, really helpful to know. Alright, so now we're going to try to do the same thing for cosine. We're going to try to find the derivative at cosine with respect to x. And so we're going to go, let's look at this graph. Alright, so we see that, alright, so we've got maxima and minima, in other words, places where the derivative of cosine of x are 0. We've got these at, so the derivative is 0 when x equals 0, x equals pi, you know, x equals negative pi, and then pi added to any of these values infinitely in the positive and in the negative directions. So, what other functions have zeros, in other words, places where they cross the x-axis at these same values? Well, we've got sine x. Look at. So, we have zeros, these values right here. We've got sine x equals 0 when x equals negative pi, 0, pi. All the same places where the derivative of cosine is 0. So this could lead us to believe that the derivative of cosine is sine. And based on the same logic as the last one, yes. However, we forgot to pay attention to this one little detail. We need to look at the slope of the cosine curve at certain places. So let's look at the slope of the cosine curve when x equals pi over 2. right here. So the slope of the derivative there, this guy, that slope is negative. I mean, that slope is quite obviously negative. So that means that the derivative of cosine at pi equals 2 should also be negative. But let's look back at the sine curve. So here we've got pi equals 2 is about here. Sine is positive. So that means that the derivative of cosine is not sine. However, what if we look at the graph of negative sine x? Alright, so here's the graph of negative sine x. And let's do an analysis of some of the values here. So we've still got zeros when x equals negative pi, 0, pi, and then those values added infinitely. But then here at pi over 2, we have a negative value for sine of x. So it would make sense, based on this analysis and not, also the numerical proof, which we're not doing right now, that the derivative of cosine of x equals negative sine x, and it actually is when you look at the numerical proof. And so now we can get a little rule kind of going, and that is, and it's the way that I like to think of it, so you have the trig functions without cos on the front of them. You have sine, tangent, sine, tangent, and secant, and they all have their derivatives. And the derivatives of the counterparts to these functions with the cos, so that would be cosine, cosecant, and cotangent, have the same derivatives as the other functions, but you add a or you add a negative for the co on it. So the derivative of sine is cosine, and the derivative of cosine is this function without the co, so just sine plus a negative. And so we'll also get, and there's not really a great graphical proof for these. I'm just going to tell them to you, and you can look in the book for the proofs. But the derivative of tangent of x is equal to secant squared x. And based on my little rule, the derivative of cotangent of x is equal to, we got a cos, we throw in a negative, and negative cosecant squared x. There you go. And I'm just going to tell you these ones. So the derivative of secant x is equal to secant tangent x. So secant x times tangent x, and then based on my rule, the derivative of cosecant x is equal to, we got a negative, and then we have the cos, cosecant x, cotangent x. So those are all the derivatives of those three trig functions that you need to know. So now that we know the product rule, we know the constant power rule, and we know the derivatives of the trig functions, I'm just going to do one practice problem with you that kind of combines all of this. And so let's consider the function f of x equals 7x squared cosecant x. And we're going to try to find the derivative of this. So, first off, we're going to have to use the product rule. And we've got these two functions right here. And what we're going to do is we're going to first leave this one alone. So we're just going to write 7x squared, and then we're going to take the derivative of this function. And if you remember, that is negative cosecant x cotangent x. And then we will add, and we're going to leave this guy alone right here, cosecant x, and we're going to take the derivative of the first bit, 14x. And so we do some rearranging, multiply stuff out. We can take out a cosecant x times 14x minus 7x squared cotangent x. And we can take out one more x here just to make everything look a little prettier. Minus 7x cotangent x. And there you go. So those are some of the most basic and most helpful differentiation formula, and stay tuned for the next video.